cohomology of real Lagrangians in the Fermat quintic. So let me give a little bit of motivation first. Homological mirror symmetry says that if X is a Calabi-Yau and if X check is the mirror Calabi-Yau, then the derived Fukaya category of X should be equivalent to the derived category of coherent sheaves of the mirror. And one of the difficulties with the Fukaya category is that it's hard to find interesting Lagrangians, and it's hard to calculate Floer cohomology for those Lagrangians. In the example I'm going to talk about today, I'm able to give an interesting class of Lagrangians and calculate the Floer cohomology from some of them. So the manifold I'm working with is the Fermat quintic threefold. So this is the symplectic manifold. This is a hypersurface in P4 of degree 5, so it's a Calabi-Yau. And the equation is x naught to the fifth plus x1 to the fifth, and so on, up to x4 to the fifth equals 0. So this is probably one of the simplest smooth threefolds that you can come up with. And one of the things you can do, or the easiest thing to do to get an easy Lagrangian, is just look at the real solutions to this equation. So let L be the set of all points in this quintic such that all the coordinates are real. And this is actually a Lagrangian because it's a fixed point set of complex conjugation, which is an anti-symplectic involution. And it's easy to see that this is actually diffeomorphic to RP3. And you can get a bunch of other Lagrangians by looking at a group action. So let me describe that group. Let G be Z5 to the fifth, where you should think of Z5 as being the group of fifth roots of unity. You can mod this out by the diagonal. And abstractly, you can think of this as lying in PU5, projective unitary group. So it acts on P4. Maybe concretely, you can think of G as being a set of points of this form: 1, comma, gamma to the A, gamma to the B, gamma to the C, gamma to the D, where gamma is fifth root of unity. And it acts on P4 just by multiplication on each coordinate by these things. So G is actually isomorphic to Z5 to the 4, and the G action on P4 is symplectic, and it preserves this equation because these gammas are fifth roots of unity, so it actually gives you a symplectic action on X as well. So G action on X is symplectic. So what you can do is look at G times L for all G. So G times L for all G gives you a family of 625 Lagrangians. Okay, so those are the things that I call real Lagrangians, and so these are the Lagrangians I'm going to be looking at. All right, and what I want to do is calculate the Floer cohomology for all these things. So here's the problem. Calculate Floer cohomology between G1L, G2L for all G1, G2, and G. So I may be missing a bunch of things. Maybe you should put some bounding cochain here, or and also a spin structure and orientation. And I'm using coefficients in Novikov ring with, say, Q coefficients. And actually, you can ask whether or not the Floer cohomology is even defined. And actually, G times L, as I mentioned before, is a fixed point set of this anti-symplectic involution, say G tau, G inverse, where tau is complex conjugation. So this fits in the framework that Professor Ota talked about yesterday. So the Floer cohomology for this thing is defined with B equals 0 as bounding cochain. All right, so I want to calculate all those. And there's obviously a law of symmetry here. You can just multiply by G1 inverse and always assume that the first Lagrangian is just L. So it suffices to calculate Floer cohomology for L and GL. Okay, and so there's also some more symmetry by permuting coordinates. So there's really not 625 different cases. There's really only like 30 different cases you have to consider. And you should think of, using the spectral sequence, you should think of Floer cohomology as lying somewhere in between singular cohomology and 0. So 0 is less than or equal to Floer cohomology, which you can think of as lying inside the singular cohomology of L intersect GL. So one way to break this down to different cases is just look at the different possibilities for L intersect GL. So let me tell you what those are right now. And actually it's easy to see that L intersect GL is equal to L intersect the fixed point set of G. So using that you can easily figure out what L intersect GL is. So there's 7 different possibilities. So first one is where you take G to just be the identity, and then you get a RP3, it's diffeomorphic to RP3, and then you can also get an RP2, you can get an RP1, which of course is just S1, you can get RP1 in a point, I'll call a point RP0. You can get a point, or you can get 2 points. And you can also get the empty set. So these are the 7 different possibilities for L intersect GL. And let me tell you the results that I've gotten so far. So in this case, RP3, the Floer cohomology, is just isomorphic to the singular cohomology. That's also going to be true in case 2. So here the notation is over here. So HF means Floer cohomology of L comma GL, and H star means singular cohomology of L intersect GL. In case 3, I know that one of these is equal to 0, and the others I don't know. So there's different G's that fall into each of these cases, and they're not all the same. So I know one here, I don't know what the others are. In this case 4, you get 1 HF is isomorphic to H1 of RP1. So I say that because that's what you get in the spectral sequence. 1 is the same thing as H0 of RP1, and there's others that I don't know. In this case, this is just going to be singular cohomology. Case 6, you have 1 is the whole thing and 1 is 0. And there's actually some others that I don't know as well. So maybe case 4 is kind of interesting because in this case, L intersect GL is RP1, disjoint union RP0, and you get some Floer cohomologies that lie somewhere in between the singular cohomology. They're not 0 and they're not the whole thing. Okay, so I wanted to keep this up. We'll see. All right, so now I wanted to describe some of the techniques I used to show this, and then hopefully I'll have time to explain how to do one of the cases in number 4. Okay, so here are some of the techniques I use. So first thing, the most basic thing, is a formula for the Nazarov index. So when you do this Floer cohomology, as it's developed in Foo, you do the Bott-Morse Floer cohomology. You look at homomorphic strips that start and stop on L intersect GL, and the L intersect GL can have multiple components. Let's say RH is one component, say RH prime is another component of L intersect GL. And then you want, for your moduli spaces, to define the Floer boundary operator, you look at holomorphic strips with top boundary on GL, bottom boundary on L, that go from one component to another. And the Nazarov index tells you the dimension of these moduli spaces, and actually it turns out to be 2/5 times what I call the weight of RH prime minus the weight of RH. So remember, L intersect GL is the same thing as L intersect the fixed point set of G. So G acts on the tangent space, and it's actually diagonalizable because it's unitary. And this weight just depends on the eigenvalues of that G action. So I don't want to write it all out, but it's something that depends on the eigenvalues. So another important thing, so this is probably the biggest thing, is there's some correlation between holomorphic strips and holomorphic spheres. So normally, if you have a holomorphic strip, so whenever I write strips and spheres, I really mean holomorphic strips and holomorphic spheres. So this is a holomorphic strip. You think of the domain as being R cross 0, 1. And this, of course, is biholomorphic to lots of different things. One of the things is a sector like this. You think of this as being a sector line at C. This line right here is sigma times R plus, where sigma is square root, fifth root of unity, so that's a 10th root of unity. And so what you can do is fill the complex plane with sectors like this. So it's going to take 10 of them. Like this, here's, if you call this S naught, here's S naught. So you have U naught, say you have some holomorphic strip, U naught. It's defined on here. The bottom boundary goes to L. Top boundary goes to GL. Because L is a real Lagrangian, it's just the real points of the quintic, and this bottom boundary is R also. You can use a Schwartz reflection principle to extend U naught to this part right here. And you can actually do the same thing all the way around. So like to extend it from here to here, multiply by G inverse, conjugate it, multiply it again by G to put it back in here. So you can do that all the way around. And what you get, start with this U naught, you extend it to a U, which is a map from, say, C union infinity to the Calabi-Yau X, and this is just P1. And that U is going to have some special symmetry from the way it was defined. And what it is this. So think of the domain as being complex plane with coordinate Z. U has to satisfy, first of all, U of gamma Z is going to be G squared U of Z. And second thing is that U of Z bar has to be equal to U of Z. And the converse is also true. If you have any holomorphic sphere that satisfies these two properties, then it has to come from some holomorphic strip in this construction. So there's exact bijective correspondence between the two things. And since U is a map from P1 to X, it's given by homogeneous polynomials that satisfy these properties. So the polynomials have some special form, which you can write down, but I don't want to right now. So another thing is conjugation of strips. So let me leave that picture there. And so let MLGL be moduli space of strips with bottom boundary on L, top boundary on GL. You can get an involution of this moduli space, so map from it to itself that sends U naught to say U naught tilde, where U naught tilde is the map defined on this part in the extension. So if you go around, the bottom boundary here is L, this is GL, and you work it out, this turns out to lie on G squared L, this is G cubed L, this is G fourth L, this is G to the fifth L, G to the fifth is equal to 1, so this has to map to L, this is going to map to GL, then you have to turn your head upside down to see that this really is the bottom boundary, this is the top boundary. So you get an involution of this moduli space like that. And you can work out orientations, work out the sign, and this. So it's a diffeomorphism. It has some sign. The sign turns out to be minus 1/2 mu of u naught plus 3/2 of some other term, which I don't want to write. This other term is not that complicated. It just depends on the eigenvalues of the g action at where it starts and stops. Okay, and since I want to use the standard complex structure, which in a lot of cases is not going to be generic for this example, you have to deal with obstruction bundles. So you have to have some way to calculate that. So let me show you what that is. Let's see how I'm doing on time. Okay, so if you have some u naught that lies in that moduli space, you look at the linearized d bar operator at u naught. Say this strip starts in the component RH at the point P, ends in the component RH prime at the component Q. The domain of the linearized operator is going to be TP RH plus TQ RH prime plus some Banach space. You have to put weights on it. It's going to have some boundary values. And here is going to be like u naught pull back Tx to LP delta u naught pull back Tx. Okay. So this is a linearized operator, and you want to look at the co-kernel of this. And this actually turns out to be a Z2 cross Z5 fixed point subspace of some cohomology group of H0 P1 U pullback Tx dual tensor omega 1. So U naught is the strip, U is the holomorphic sphere that you got from the strip. And remember that the holomorphic sphere had this Z2 and Z5 symmetry that I wrote down. And this would be the obstruction bundle for the holomorphic sphere. And if you look at the obstruction bundle for the U naught, you want to look at just the Z2 cross Z5 fixed point subspace of this cohomology group. Okay, and so the last thing I need is a spectral sequence. This is from Fu. And so to calculate HFL GL, you have the spectral sequence available, and the E2 page of this spectral sequence consists of all the singular cohomology groups of L intersect GL. So there's going to be lots of notation that I don't want to explain, but let me write it down. So right down here, this should be F lambda P minus K 0. No. All right, so the important things here are this H is singular cohomology, this RH is a component of L intersect GL, and this HW is some homotopy class. You're summing over all these things, so you're basically going to get singular cohomology of L intersect GL in there. This is some local system, and this is Novikov ring coefficients. There's two gradings on it. This grading is by Nazarov index. This grading is some sort of energy filtration gradient. And basically what we're doing here is if you have the Floer boundary operator, you can break it down as this, say like delta equals delta naught plus delta 1 plus delta 2 and so on. And this delta is the singular cohomology. So that's the part we use to get to the E2. That's why there's singular cohomology groups there. And then these ones are all the higher energy ones. So like the delta 1 is going to be the lowest non-zero energy moduli spaces are used to, the lowest energy moduli spaces are used to define delta 1, and then the higher energy ones define the higher energy parts. And the maps on the E2 page are going to be defined using this delta 1. So to see what the maps are on the E2 page, you just need to describe these lowest energy moduli spaces. And the trick is, using all these other techniques that I wrote down, you can actually explicitly calculate what those things are, and that turns out to be enough to calculate all these Floer cohomologies that I mentioned. Okay. All right, so now let me show you how the calculation goes in some of these cases. I'll do cases 1, 2, and 5, and one case from 4. I use this case right here. All right, so cases 1, 2, and 5, these are actually pretty easy. So in cases 1, 2, and 5, L intersect GL has only one component. And if you remember that formula that I wrote for Nazarov index, the Nazarov index of some strip is going to be, it was like -1, 2/5 weight of RH minus weight of RH prime, where this weight had to do with the eigenvalues of the G action on that component. There's only one component. These two things are going to be the same. And what am I doing? There's no there's no -1 here. Sorry, it's just this. The other thing was a change of sign. So this is the Nazarov index, just this number right here. So if there's only one component, these two numbers are the same, so it's just 0. So now you look at the spectral sequence. What you have is, say you have some S in say H star L intersect GL. What you want to do is you want to calculate delta of S, where delta, I guess, is just the contribution coming from the higher energy things. So the moduli spaces that come into play here, their dimension is governed by the Nazarov index here. And so you can actually calculate what the dimension of delta of S minus the dimension of S has to be. And it actually has to be Nazarov index plus the dimension of the component it ends in minus the dimension of the component it starts in minus 1. There's only one component, so these two are equal. So this difference is 0. This is 0 from over there. So this is equal to -1. So in other words, the Floer boundary operator changes the dimension of a cocycle by 1. So in order for the map to be non-zero, there has to be cohomology in 2 consecutive dimensions. And you see in cases 1, 2, and 5, there is no cohomology in consecutive dimensions, and so all the terms in spectral sequence are just going to be 0. So it degenerates at E2 page, and you just get singular cohomology of L intersect GL. Okay, so that one wasn't so bad. Now let me describe the one from case 4. This one's a little bit more interesting. I think I'm going to do this one right there. All right, so I can erase this now. So case 4. Where the HF turns out being H1 RP1. Okay, so the G that will give you this, or one of the G's that will give you this, is G equals 1, comma, gamma, comma, gamma, comma, 1, comma, 1. Then L intersect GL is RP1, disjoint union RP0. This RP1 comes from the points of the form like x naught, 0, 0, x3, x4, that lie in x. And this RP0 is just the point 0, 1, minus 1, 0, 0. So if you look at the spectral sequence, you have singular cohomology of that. So that's 3 non-zero things. So you're going to get a E2 term, you're going to get an H1, RP1, H0, RP1, and also in a H0, RP0. And using the formula for Nazarov index, you can see there's only going to be 2 maps that could possibly contribute. There's going to be a map here, and there's going to be possibly a map there. Just for dimension reasons, you can see those are the only ones that there can possibly be. So now let's try to describe the lowest energy moduli spaces. Here is RP1, here's RP0. So lowest energy things are given by lowest degree polynomials that you can find. And actually, it turns out to look like this. So if you pick any point here, there's going to be a 1-parameter family of holomorphic strips that start and stop at this point. And also, they happen to go through this point here. So this is some holomorphic strip. There's a 1-parameter family of these things. If you go in one direction, it's going to degenerate to a sphere with boundary lying on, actually I forget, I think either L or GL. If you go in the other direction, it's going to degenerate to a broken trajectory. So there's going to be a broken trajectory like this, one that goes from here to here, and another one that goes back. And it turns out that this thing is given by degree 5 polynomials. The one that goes back is given by degree 3 polynomials. And the one that goes here to here is given by degree 2 polynomials. And this map from H1 RP1 to H0 RP1 is given by this moduli space, things that start and stop on RP1. And this map from RP1 to RP0 is given by this moduli space, things that go from here to here. And actually I lied, there's not, for every point there's not this 1-parameter family. Actually, for every point there's 2 1-parameter families. And they all fit together to give you non-trivial double cover of this picture that I described. So this moduli space here, degree 2 things, moduli space is actually isomorphic to S1. If you evaluate at minus infinity, you get a double cover of this RP1. So now let's try to figure out what the maps are in the spectral sequence, the E2 page. This thing has degree 5, so it's bigger, has more energy than this one. So on this page, it's not going to come into play. So this map here is just going to be 0. And then the map from H0 RP1 to H0 RP0 is basically what you do is take a point class here and take intersection product of that point class with ev minus infinity push forward of S1. That gives you some number, and that's multiplication by that number is what this map here is. And this is just double cover here, so this map is plus or minus 2. So then this is E2, go to E3, take cohomology, this is going to disappear, and you're just going to be left with H1, RP1, and then there's no more maps. And that's it. So that implies that Floer cohomology is isomorphic to H1, RP1. Okay, and I'll stop there. Thank you.